this is a bit of a warning, that special relativity really contradicts common sense. So all the ideas that we'll talk about are really hard to understand because it's things that we don't see every day. It's something that's not very intuitive at all. So if you're confused by what I'm going to talk about, that's okay. This is really kind of hard stuff to wrap your head around. So I'm going to try to be really careful and precise in walking through what special relativity is really all about. So before we start with talking about the weird effects of special relativity, we have to stand back and first talk about reference frame. So a lot of times in physics we talk about velocity or speed, and everyone has a pretty good intuitive feel for what speed is. Right? But in relativity, we have to be very careful when we're talking about speed. We always have to specify or be very particular with our reference frame or our point of view. An example of this, in Sydney, for example, you might say that I'm on the M4 highway driving at 100 kilometers an hour. Now, as soon as we all have an idea what that is. You can picture that car moving down the highway at 100 kilometers an hour. But we should be a little bit careful in that because we realize that our speed actually depends on our point of view. So our speed relative to a billboard, for example, that's in the distance, we're driving towards that billboard at 100 kilometers an hour. Right? That would be our speed relative to a billboard. But let's say that your friend is sitting next to you in the car, and you ask, how fast am I going now? Well, your speed relative to a passenger in your car is 0. They're just sitting there in the car right next to you. So in the reference frame, what we call the reference frame of your car, your friend is not moving at all. There's a billboard moving toward you at 100 kilometers an hour. And we can keep carrying on with this. Another example would be maybe relative to, look at your speed relative to oncoming traffic. It's also moving at 100 km. That traffic will be moving toward you at 200 kilometers. So we can see that speed, when we say that speed is relative, this is what we mean, that we have to be very careful, specify our reference frame before we start talking about speed. One final point here is that we really can't tell, when we say I am driving at 100 km an hour, you could also say that the billboard, for example, the billboard, that I'm sitting still in my car and the entire world is moving underneath me at 100 kilometers an hour. Those are basically saying the same thing, but there's a slightly different way of looking at it. So your speed, for example, of the billboard relative to you is 100 km an hour. And we'll get back to this point again, but just keep in mind that that speed depends on your reference frame. So you have to be very careful. Now, in special relativity, we only talk about very special kinds of reference frames. We talk about inertial reference frames, and the definition of an inertial reference frame is one that is moving at a constant speed relative to another reference frame. So the example of you sitting in a car, provided that you're traveling, maybe you have your car on cruise control, you're traveling at a constant speed, you can say that I'm in an inertial reference frame in my car. And so all the principles of relativity we'll talk about today are only to do with reference frames moving at a constant speed. You can imagine that you're going 100 km an hour and all of a sudden you have to put on the brakes and start slowing down. Now your reference frame is no longer moving at a constant speed. It's decelerating. And for that, you have to consider a whole different kinds of mathematics and physics called general relativity, which we won't talk about today. So again, we're just talking about special reference frames or inertial reference frames. So, finally getting to the principle of relativity, it seems very simple, and this is what Einstein wrote down in the early 1900s. He said that the laws of physics are the same in every inertial reference frame. So this seems like a pretty simple idea or simple concept. Really what he was saying is that if I do some experiment in a car, the same experiment, I should get the same result if I do that experiment in a different reference frame. So I have an example. Imagine that all of you sitting in a classroom had a cricket ball, and you had a simple experiment to measure the Earth's gravitational force on a cricket ball. You can do that in a lot of different ways. You've probably done it maybe in some of the physics lab. Now, let's imagine then that your friend does the same experiment. They take that cricket ball, but your friend is getting on the train, gets on a train. The train is moving at a constant speed. What this principle tells us is that your friend will measure the same force on that cricket ball. So in other words, it doesn't matter if you're moving at a constant speed or maybe at rest relative to another reference frame. The laws of physics are always the same. And I tried to convince people of this because it wasn't really obvious. It's just kind of an idea. It doesn't necessarily have to be true. You can imagine that maybe if you were on a train, you get a different gravitational force due to the cricket ball. But he said that as long as we're dealing with inertial reference frames, and one's moving at constant speed, we should get the same result. So the law of gravitational force is one law of physics, but another one has to do with electricity and magnetism, and that is that light always travels at a constant speed. So in a vacuum, we know that the speed of light, usually we call this c, is about 300,000 kilometers per second. That's one law of physics that we have to obey. If we want to obey this principle of relativity, it tells us that no matter what reference frame we're in, we have to measure light to always have that same value. And this is where things start to get weird, because this implies that light travels at this speed c in every inertial reference frame. But we can put this another way. What this means is that the speed of light is now independent of the speed of the source of light. Because someone measuring light, well, I'll just show an example of it. So we're going to think about two inertial reference frames. We'll call one reference frame S, and this will be, just because we need some label for it, this reference frame is an observer at rest on Earth. And I have another reference frame here called S prime or S tip. This is a reference frame, is a spaceship moving at a constant speed. So I have a picture here. Here we have the Earth. We have an Einstein sitting in a chair. Einstein is in this reference frame S, sitting at rest on Earth, and he observes a spaceship. The spaceship is moving 1,000 meters per second, say, relative to Einstein. That's fine. And now we'll say that this spaceship fires a missile. And it fires a missile at a speed of, say, 2,000 meters per second relative to the spaceship. So the pilot of this spaceship sees this missile go off at a speed of 2,000 meters per second. And we can ask, well, how fast will Einstein see that missile move? And the answer is 1,000 meters per second plus 2,000 meters per second. You just add those two speeds together. So that kind of scenario, it makes intuitive sense. If you were, you just add up the speeds together to get the final answer. Right? And so here it's just saying that this is very simple or Newtonian mechanics, the laws of motion that Newton came up with. But now we're going to change things a little bit. Now we'll imagine that, again, we have our spaceship moving at 1,000 meters per second. Here's Einstein looking at it. Now the spaceship shoots out a light beam. And the spaceship is going to shoot that light beam out. It has to shoot that light beam out at a speed of c, right, 300,000 kilometers per second, relative to the spaceship. So again, a pilot sitting in the spaceship will see that light beam go out at the speed of light. So now we say, okay, well, what will Einstein observe? Well, if we use our other example, we would say, well, you would see the speed moving at c, the speed of light, plus 1,000 meters per second. But this is where it gets weird. That all of a sudden, that violates our principle of relativity. Because we've said that the speed of light always has to be measured to be c, no matter what reference frame we're in. So we can no longer add together those two speeds. We have to do something else. So how can we make sense of this? Well, I started off at the beginning saying that speed depends on our reference frame. It depends on we're on a train or in a car, so forth. And just by definition, we know that speed is distance traveled per unit time. So our challenge here to make sense of this is to somehow come up with ideas that allow us to always measure the same speed regardless of the speed of the source, of our source speed. And the only thing we can do is play around with distance and time. And so to get around this whole issue of the constancy of the speed of light, well, to be more specific here, so in order for the speed of light to be measured to be constant in all these reference frames, then distance and time itself must be stretched or compressed in different reference frames. It must have a different meaning. So our concept of distance and time now depends on our reference frame. Because we can no longer put, we know that the speed in the case of light always has to be the same number. But we would say, well, what if I'm traveling, this is the experiment that Einstein thought of, was what if I were looking in a mirror, but I were moving near the speed of light? Let's say that I was moving away from a mirror, close to the speed of light, what would I see? And the principle of relativity says that, oh, well, you just see, it would be normal to you because the speed of light is the same in every frame. But in order to really make sense of it, we have to change our ideas of distance and time. So I'm just going to go through one of the consequences of relativity, which has to do with time. And we'll go through this pretty carefully to see where there comes a formula that you'll see when you're talking about special relativity, or where they come from and how to use them. So we'll start by thinking about an observer in a reference frame. Well, we need to label all of these things. So we're only going to think about two reference frames to keep things simple. So our first reference frame we're going to call S0. So we have an observer at rest in a reference frame S0. And imagine that they observe two events, and it takes some time t0 between those two events. Now we have to add another clause here, which is that those two events happen at the same point in space in that reference frame. So this is very generic. One specific case would be, imagine that you're sitting on a train. You get on the train, it starts moving, and the train is moving at a constant speed, and you have a coffee. And because you were clumsy or whatever, you spill the coffee on yourself. So let's think of that as two events. One event, the coffee is just about to fall out of your cup, say, and the second event is you have coffee all over yourself. Now, relative to you sitting on that chair in the train, right? That happened at the same point in the train, at the same point in space. So that's what we're just describing here. Now let's look at this spilling coffee from a different point of view. Let's imagine an observer in a different reference frame, let's say standing on a platform, the train platform. We're going to call this reference frame S sub v, because we're going to say that reference frame is moving at a constant speed v relative to our reference frame up here at 0. So, getting back to the coffee example, if your friend, an eyewitness, is standing on the train platform, and they can see into the train, and they see you come by, let's say like this, let's say you come by from left to right. As the train comes by, let's say at this point you start to spill your coffee, and over here the coffee has hit your lap. So from the point of view of the person on the train platform, they can see that coffee hit your lap, but they would see that event happen at a different point in space. Because that train is moving, they first see the coffee start to spill at one point of the platform, but then it hits your lap at some other point along the platform. So the first point is that this observer in this red colored reference frame, this X sub B, sees those events happen at two different points in space. This is a real key thing when you work out a lot of the formulae for special relativity. You have to keep all of this in mind. Be very careful when you're talking about this. So the observer on the platform will see the coffee spill event. Those two events happen at different points in space. And if you're careful and draw out this diagram and apply the principle of relativity, you can also show that the time that it took for that event to occur will be different for the person on the platform than it is for the person on the train. And in particular, you can show that those two events will happen over a longer time interval. We'll call that longer time interval T sub B, that's in red. And it's related to T0. That was the event taking place in the reference frame of the train. They're related in this way. So it's T0 divided by square root of 1 minus V squared over C squared. And this is a longer time interval. This number is bigger than T0. And it's just a consequence of having to ensure that no matter how fast you're moving, that the speed, that if you were to emit light, it would still be at a constant speed. So our example of a train moving and spilling coffee on a train, you would think that this doesn't make any sense. How could time slow down? Like I see the person spill the coffee and that's fine. But if you say, well, now let's imagine that train is traveling close to the speed of light, then this becomes a much bigger effect. In general, this is called time dilation, because what it means is that events that occur in one reference frame take a longer amount of time than in another, or that clocks slow down. So this effect of time dilation is very weird, because it means that clocks will move at different rates in different reference frames. And we always like to think that, well, I know what 1 second is, and I sit here and I watch time move by on my watch, and the person who's driving in the car down the road here, I assume that their clock is moving at the same rate as my clock. But special relativity is telling us no. In order to obey the principle of relativity, the rate at which time passes is different depending on your speed. And that's very weird. So if we look at, we have that formula for time dilation, we can see that this is only a big effect if we're moving near the speed of light. And some numbers here. If, for example, if you're moving at 1% of the speed of light, you would only see this time stretching by a factor of 1.00005. Very small. If you were moving at half the speed of light, you would see that the difference in the rate that time passes is about 15% or so. So, again, you have to be moving very fast, and the speed of light is very fast, but this is measurable. We'll go through a specific example of this. So we'll see how this really, how you might be able to measure this, and we'll see the magnitude of the effect. I'm going to use an example of flying on a plane or a spaceship. So the example here is Queen Elizabeth. Here I say Queen Elizabeth the 20th. Let's imagine we're 100 years in the future, and she's on a spaceship flying from London to Sydney. So it's a distance of, say, 18,000 kilometers. She's on a spaceship that's moving at a constant speed at 1% or 10% of the speed of light, or 30,000 kilometers per second. So she's moving pretty fast. The questions that we want to ask are, how long does the trip take measured by an observer on the ground? And how long would the trip take measured by an observer on the spaceship? Now, common sense would tell us, well, it's going to be the same number. It doesn't matter how fast it moves. But special relativity tells us that it's not true. So let's see, I'm going to go through and try to work this out. So we want to keep that general description of reference frames in mind. And for this problem, first I want to identify the events that are taking place. There are two events. Event 1, the Queen leaves London. Event 2, the Queen arrives in Sydney. That's okay. But now, let's look at reference frames. Now we want to identify who's in what reference frame. Well, from the point of view of an observer on the ground, those two events, and it leaves London, arrives Sydney, take place at different points in space. So that means that an observer on the ground would see a plane take off or a spaceship take off from London and arrive in Sydney. And those events happen at different places in space. So if we refer back to how we wrote down our equation before for time dilation, this means that our observer on the ground is in this rest frame S sub B, this red colored reference frame. We're seeing events take place at different points in space. So the other reference frame is the Queen's reference frame, so an observer on the spaceship. Now from her point of view, these two events, leaving London, arriving Sydney, take place at the same point in space. Now this seems, again, this is one of the weirdnesses of special relativity. You would think, well, no, wait, those two events one happened in London, one happened in Sydney. Those are different places. But when the Queen got on that plane, that spaceship, and sat down in a chair, and then didn't move, she sat there, waited for a while. Well, in this case, she doesn't have to wait very long because she'll get to Sydney pretty fast. But from the reference frame of the spaceship, she hasn't moved at all. And what has happened is that the Earth has appeared to move underneath her, and then all of a sudden, at one point, she was over London, and some time later, she was directly over Sydney. That's how we have to think of these reference frames in order to work out the effects of special relativity. So using the language from before we set up our problem, again, this observer on the spaceship observes these events at the same point in space. So that means that observer is in this blue reference frame, x0. We now have our two reference frames. Now we can start putting some numbers in. So the first part of the question asks, how long do those two events take place from the point of view of an observer on the ground, S sub B? Well, they're going to measure this time. We're going to call this time, remember, we call this time T sub B in red. That's just simply the distance traveled by the Queen divided by her speed. So in this case, it's 18,000 kilometers divided by 30,000 kilometers per second. You can see that an observer on the ground sees the Queen travel from London to Sydney in a bit more than a half a second, 0.6 seconds. That's pretty fast, but she's traveling at 10% of the speed of light. Right, so that's our time between those two events from this in this reference frame SD, or observer on the ground. Now let's go to the other reference frame, the observer on the spaceship. Now the Queen is going to measure a time between those two events. Remember, we call this one T0. And we had our formula that related T0 to T to B. And I've just rearranged it now to see what we get. So now we know what T sub B is. We just worked that out. That was 0.6 seconds. Again, that's the time as observed by someone on the ground. We know what the Queen's speed is, V, 10% the speed of light. When we put those numbers in, we see that the Queen observes that trip to only take 0.597 seconds. It's actually a bit shorter than the time observed by someone on the ground. So we put these two numbers together, we see observer on the ground measures 0.6 seconds, observer on the spaceship measures 0.597 seconds, something like that. So this means that time, well, what we think of this as, we can explain this by saying that time has passed by more slowly on the spaceship. So if we were to somehow get access to two clocks at the same on the plane and on the ground, what we're saying is that the clock on the spaceship is moving more slowly than the clock on the ground. That's just again a consequence of this very simple principle of relativity. Now, you might think, well, this is just kind of silly because we don't have spaceships that can travel the speed of, you can't get from London to Sydney in half a second. That's ridiculous. But physicists have put very accurate clocks on actual regular airplanes that travel more like, I don't know, kilometers per second, going maybe 1,000 kilometers an hour, much slower than this. Put very accurate clocks on a plane, put a very accurate clock on the ground, and do this experiment, and they verify that this is true. So they actually see that the clock on a plane will move more slowly. Now, at speeds of a regular airplane, the difference between those clocks is very, very small. But we have very accurate clocks, and you can actually measure this effect. So it's really seen by real clocks on real planes. There's just a few tips and tricks for solving problems in special relativity. One is that it's very easy to confuse reference frames. So I tried to get to a bit before. And the problem is that it's not really correct to say that you're moving, I'm sitting still. Because from the point of view of the other person, they'll say, no, you're moving, I'm sitting still. So each reference frame sees the other one as moving. So you have to be really careful in thinking about these kinds of problems. So this example of the Queen moving from London to Sydney, we put her in reference frame S0 because those events took place at the same point in space, even though one event happened in London, the other event happened in Sydney. We would have gotten it wrong had we put the Queen in the red reference frame, S sub V, and put the person on the ground in the other reference frame. We get the wrong answer. So they haven't been followed sort of the rules that we use to get to that equation about time dilation. So it's very common to use the wrong numbers in those equations. And so a way to make sure that you don't get into trouble, at least for this time dilation, is to first identify the two events. Usually there will only be two events, so we'll keep it simple. Then identify the reference frame where those events happen at the same point in space. Here I've been calling those things S0 and time T0. Then you identify the reference frame where those events happen at a different point in space, S3 and T sub V. And then depending upon what you're given for that particular problem, then you just apply that formula for time dilation. Not quite right. So this is one of the last slides now. I don't have time to go through all the other weird effects of relativity. So I've only been talking about time dilation. But it's possible to start from the principle of relativity and show a lot of other really cool things. One is it's called length contraction, and that's an effect where the distance between 2 points changes with speed. So our example of the Queen, if she were to be carrying a standard meter stick with her, and as she travels close to the speed of light, an observer on the ground will observe that meter stick to actually shrink the faster the Queen moves. That again is to account for, because speed is distance over time, we have to rethink our ideas of distance and time together. So that's called length contraction, and there are formulas that describe this effect of length contraction. Another effect is that mass no longer is constant, and mass increases with increasing speed. So this comes up. So if we're playing around with distance and time, if we then go and try to say, well, what is we can start with Newton's laws of motion and say, well, what is the momentum of something moving near the speed of light? And momentum is mass times velocity. And velocity, again, gets very weird. So you can actually show that now mass can change with speed. Mass dilation is another formula that describes that. You can also show this is a very famous equation that Einstein came up with, this E equals mc squared. That comes just from thinking about special relativity. And what you can show is that a mass that's sitting still or at rest in a reference frame must have non-zero energy. The only way that you can get all of these ideas to be consistent with one another. And we show that the so-called rest mass energy of something is mc squared. A couple other things that you can show is that if you have anything that has mass, so we think that, well, we know that light, sort of by definition, doesn't have any mass. It's a bit weird. It carries energy, but it has no mass. And if something doesn't have mass, it has to travel at the speed of light. But if you do have mass, then there's a rule that you can show from relativity that you can never reach the speed of light. So it's impossible, something that has a non-zero mass cannot be accelerated to the speed of light. In fact, you can show, it's pretty fun sort of exercise to show that it requires an infinite amount of energy to accelerate something that has mass to the speed of light. And finally, one of the other strange things with relativity has to do with simultaneous events. So here I'm just saying that the concept of simultaneous events is limited. So what I mean here is that we all have sort of an intuitive feeling of two things happening at the same time, right? If the bell in the classroom at your school is going to go off at exactly 11 a.m., you would think that, well, if all the clocks in the state of New South Wales are synced, and there's a bell that goes off in another school at 11 a.m., that we have a pretty good sense, we can understand that. You're like, yes, those things happen at the same time. But if one of those events is happening in a reference frame that's moving relative to another one, now that suddenly doesn't make sense anymore. In fact, we have a very limited way of describing what simultaneous really even means. So these are all the weird things that come out of special relativity. You might think this is all just pretty fun, or it's hard to understand, but kind of fun to think about, but it doesn't really have anything to do with you. There's a lot of practical applications. One of them is the Global Positioning System, or GPS. You have a mobile phone with GPS on it. It is calculating the effects of time dilation, because it's, in order to work out your position on Earth, it's using the signal from satellites that are moving in orbit around the Earth, and they're moving pretty fast. They're moving fast enough that you have to worry about this. And so your mobile phone does have the equations of special relativity inside of it. If it didn't, it would be off by quite a bit. It wouldn't be very accurate. A couple of other practical applications are particle accelerators. So an example is the Large Hadron Collider, that you might have heard about in Switzerland. This is this giant ring underground that is accelerating particles to near the speed of light, smashing them together to see what they're made of. You really have to worry about special relativity there, because you have particles like electrons and protons that are moving near the speed of light, and so you have to account for that when you want to interpret the experiments. And closer to what I do every day, as an astronomer, I'm looking for signatures of exploding stars and black holes using radio telescopes. And sometimes black holes like to form these jets of material that shoot away from a black hole at very near the speed of light. And in order to interpret those observations, we have to use the equations of relativity in order to work out the energy and the interactions of the particles in the jet.